So, good morning, everyone. And today we are covering lecture 12, I think, which has two big topics, power system control and economic dispatch. By the end of the day, we will understand how grid operators manage power flow on transmission lines, how to calculate, um, just give me a second to fix this. So how to calculate how much a generator change affects a specific line and how we decide which generator to use to meet the load at the lowest cost. Now, without further ado, let's get started. Now, the first thing I want you to understand is why controlling a power system is hard. Transmission lines have thermal limits, if you may recall from the previous lectures. If too much current flows, the wire heats up. And do you remember what we called that? The heating of, it has a limit. We call it the sagging limit. So the line sags and can cause a fault. So again, the most important limit that we have is thermal limit. When it gets too hot, basically it's melting, it starts melting. And the problem is there is no direct way to control how much power flows down a line because we don't have any control on the loads. And unlike for example, a water pipe, you cannot close a valve. So in a water pipe, you can close the load of valve and control it that way. But power flows follows physics laws, specifically Kirchhoff's laws. And the Kirchhoff's laws decide where it goes, not the operator. A simple example would be if we have lower resistance, you're going to have higher current passing through that branch. So we don't have any controls. But for a water system, you can, control the valves and control the loads and the outputs. So the Kirchhoff law decides it, where it goes, not the operator. So the only way to change the flow on a line is how can we change the flow? Again, we don't, this is a vertical system. Again, it's not a smart grid. We don't have any control on the loads. The only thing that we have control on is what? The generators, perfect. So the only thing that we can change on the line is what we can change on the generators and what the generators are doing. And that's an indirect control we are going to study today and go through today. Now, here is a specific question we want to answer in the slide. Suppose we have a generator at bus K and we want to know if we increase the output of the generator, how much does the power flow change on the line between bus I and bus J? So again, we don't have direct control between bus I and J, and we want to see if we can change the generator PJK, how much it would affect the power flow between bus I and J. That ratio, the change in the line flow divided by the change in the generator output, is what we call a sensitivity factor. One important assumption that we have here and we're making here is that whenever we increase generation at bus K, the slack bus automatically decreases by the same amount to keep the system balanced. The slack bus absorbs the difference. Again, because of the Kirchhoff's current law and we don't generate extra power, it must be all the power that is generated, it must be consumed, in other words. Now, this is an interesting example for a 3-bus system. Here we have a specific questions that we want to answer. suppose we have three-base system. Oh, yeah. I want to show you the before and after. Okay. And in this example, we have three bus systems as mentioned. And for a moment, look at the flows on the lines. What do you immediately see? So imagine that you're an operator of this system, okay? And we have three bus. First of all, which bus has generator connected to it? Which buses have generators connected to it? Do you remember the sign for the generators? So this one and this one, yes? These two are our generators. And what about bus 2? That's the load. So the arrow is the load. So bus number 1, bus number 3, and bus number 2. Okay. Now, immediately you would see a problem here. Can you point out to the problem? Yes, there's an overload. Where is the overload? Between bus 1 and 2. So, and again, this is a kind of situation a grid operator sees in real time, and this is a real-time software simulation. Now, the question is, what can we do about it? Again, we cannot physically block this flow because we don't have any control. It's not like a valve that I can, turn halfway between bus 1 and 2. What can I do? So the only part that we have control are which buses, which parts? These generators. Yes. So the only thing that we can control is the generation dispatch or the output of the generation. But to know how much to change it, we need to know the sensitivities, what we call a sensitivity. And let's see what happens when we actually change a generator. So this is a before situation. Now let's change the generation, the power generation. Now, in this after scenario, we have increased generation at bus 3 by 95 megawatts. The slack bus at bus 1 decreased by 95 megawatts. Now we look at what happened to the line flows. The flow on the line from bus 1 to bus 2 went from 131.9 megawatts to 101.6 megawatts. So how much did it decrease? By 30.3 megawatt, it has decreased. Okay. And the flow from bus 1 to bus 3 dropped to how much? Again, bus 1 to bus 3. How much was it before? It was 68.1, and it dropped to how? To 3.4. So how much did it drop? About 64 megawatts. To be exact, 64.7 megawatts this dropped. So this one dropped and this one dropped. And if we express these as a fraction of the 95 megawatts, so 30.3 divided by 95 would give us around 32%. And 64.7 divided by 95 gives us about 68%, almost 68%. Now, if we add these two, what is 32% plus 68%? Gives us 100%. Am I correct? And that makes sense because all the 95 megawatt has to go somewhere. We can't just evaporate into air. It's because of the physics and the Kirchhoff's law that we have. And these percentages are what we call sensitivity, or in other words, sensitivity factors. So for every 1 megawatt we increase at bus 3, the flow on line 1, 2 drops by 0.32 megawatts, and the flow on line 1, 3 drops by 0.68 megawatts. So what we have done, we have just changed one of the generators, and then you can see it affects the whole system. Okay. Now, let's go to the analytic calculation of sensitivities and how we do it. The previous case was only for 3 bus. Now imagine what when we have like 500 bus and 1,000 lines. It's not that easy that you can simply, calculate them. So for running a full power flow before and after every possible generator change, it's going to be very slow using the previous method. And if we have, as mentioned, hundreds of generators and thousands of lines, it's not practical in real time to do so. So instead of running simulations, we calculate these sensitivities values analytically, directly from the network equations. We do one matrix inversion and we get all the sensitivities at once. And this is what makes real-time control possible. And these are the equations that we use for the power flow from bus I to bus J. And we want to find delta P and delta theta over delta P. And why do we have delta PJ GK? Because we can only control the generation side again. Now, here's the math behind it. We use the DC power flow model. The key, and you already learned about DC power flow model in the previous lectures. The key matrix is called the B prime. And as you may remember or recall, the B matrix is the susceptance matrix. With a slack bus row and column removed, we inverted B prime once. Then for any line from bus I to bus J and any generator at bus K, the sensitivity is equal to the line susceptance times the difference between the ith and the jth rows of the prime inverse, evaluated at column K. And it looks like a lot, but the key point is to invert once, get all the sensitivities. This is the fundamental part of every system that we have, and that uses real-time operations. Just does this, and you have to do the matrix and calculate once the inverse, and you're done. Now let's work through the 3-bus example numerically. The previous one that we did, let's do it numerically instead of having the simulation. So we take the line reactance, we compute the, what we do is we would compute the susceptance, build the B matrix, and remove the slack bus row and the column to get B prime. So what we do is we remove slack bus row and the column to get B prime, which is here, and this one. And next step we have to inverse the B prime. So we will invert it, and then we would apply the formula that we have. And when we do this for the 3-bus case that we saw earlier, the sensitivity for line 1, 2 with the generator change at bus 3 comes out to about 32%. And for line 1, 3, it comes out to about 68%. And you can see here, what we got numerically, it's 0.66, which is very close, almost identical to 68%. And the other one is around 32%, which matches exactly what the simulation showed us. That is our verification that the analytic approach works in this scenario. Again, instead of going to the simulation, it takes a lot of time. When you have hundreds of generators, you can do it numerically. Now, this is a realistic situation, and it is a 37 bus system with 2 lines already out of service. Because of those outages, there is an overload on the line between Pier 69 and Pecan 69. This is exactly the kind of emergency contingency that real operators deal with. We are going to use the sensitivity approach to figure out how much we need to change generation to fix this overload. And the answer will be an approximation because we are using the linear DC model, but it's going to be close enough. It's going to be the previous, like the previous one that we got 0.667, which was pretty close to 68, and 0.33, which was pretty close to 32%. So again, it's going to be an approximation, but it's very close and useful in practice. Now, what we do here, as mentioned, and you can read faster than I can on the slide. So we increase generation at Orange 69 bus by 10 megawatts. Orange 69 is here. If you zoom in, you can see all of them. And before the changes, the overload line is carrying 121.4 megawatts. And after the change, it drops to 116.1 megawatts. So the flow changed by negative 5.3 megawatts for a 10 megawatt generation increase. The sensitivity is negative 5.3 divided by 10, which is 0.53 of 53%. That means for every 1 megawatt we increase at Orange 69, the overload line drops by 0.53 megawatts. If we need to reduce the overload by, for example, 20 megawatts, how much do we need to increase the load, the Orange 69? So the question, let me do a question. So we learned for every 1 megawatt that we want to decrease, the overload line drops by 0.53. Okay. Now, if we want to drop the overload by 20 megawatts, how much do we need to increase Orange 69? Okay, so 53% of the increase in Orange 69 would create a drop, 20 megawatt drop. Okay, so 20 megawatt is 53% of that increase. So how much is that increase? So divide 1 by 50.53 and multiply it by 20. It would give us less than 40, like 38. 38. So that increase would be 38 megawatts. Okay, thank you, Tyler. Okay, now let's shift to reactive power. Reactive power is also very important. I'm sorry, I accidentally moved this. Anyway, I'm gonna skip. So now let's shift to reactive power. Now, reactive power control is done through switch capacitors and reactor banks. And static volt-amp reactive compensators as well. And also load tap changing transformers and sometimes generator voltage set points. And the goal here is to maintain proper voltage across the system and reduce losses. Reactive power is much harder to optimize than real power because relationship between Q and voltage is highly nonlinear. Especially when you get close to voltage collapse and The other thing is reactive power does not travel efficiently over long distances. Why? Because transmission lines have much larger reactance than resistance. So reactive loss are higher. Now, this is a very interesting real world example that illustrates how important reactive power is. The Zion nuclear plant in Illinois, it was a 2,000 megawatt or 2 gigawatt facility. In 97, during a plant shutdown, an operator pulled the control rods out of sequence, a procedural violation. The NRC cited too many people in the control room and improper procedure. The cost to fix the damage alone was estimated to be $435 million. And Comet, the operator, decided it was cheaper to just permanently shut down the plant than to repair it. So you can see $435 million was lost just for a small operator's mistake. Not a small one, but just not following the procedures. And the operation room, as again, was crowded. They couldn't see the alarms, and the system failed. And again, the cost of repair was more than to build a new one. But there's an interesting part to it. The interesting part is the plant's generators were still used for years as reactive power sources for northern Illinois, even with no nuclear fuel. And that tells how valuable reactive power support is to the grid. So you can see, even with no nuclear fuel and not working, they still use it as a reactive power system. Now, this slide shows the Zion plant on Lake Michigan, right on the Illinois-Wisconsin border. You can see why nuclear power plants are sited near large water bodies. You know why we usually put them, the nuclear power? Yes, perfect. Because of the massive cooling capacity that's needed. The plant is now in the process of full decommissioning, which itself takes decades and is a significant engineering undertaking. It costs a lot because it's a nuclear power plant. So now, in a deregulated power market, generators and loads enter into contract called power transactions. I already mentioned a little bit about this in the introduction class. A transaction is simply an agreement to move a certain amount of power from the seller to the buyer for any duration at a negotiated price, depending on how many generators we have. Sometimes for example, some markets we have monopolies. Here we have Exo, but if you go to Houston, Dallas, it's going to be different pricing because you have different generators and so on. So there are regulatory bodies that set the price for markets that only have one supplier, for example. Now, these scheduled transactions gets entered into energy management system as a scheduled interchange value. This value feeds into the area control error calculation, which is what the automatic generation control system uses to keep generation matched to load in real time. Now, PTDFs are, in other words, power transfer distribution factors, or what we call PTDFs. They extend the sensitivity concept to transactions. Instead of asking how a single generator change affects a line, we ask if power is being transferred from point A to point B, what fraction of that transfer flows on each transmission line. A PTDF is just the difference between the GSFs at the sending bus and the GSF at the receiving bus. So PTDFs are calculated using the same B prime matrix approach we already covered. Every independent system operator, or what we call ISOs, if you remember ISOs, in North America publishes PTDFs so that the market participants can see how the transaction will load the transmission system. Do you remember the Enron effect and the pricing gouge and everything? It's because of that, a little bit of that. Now this slide shows a 9-bus PTDF example. And in this slide is showing the initial power flows on each line before any transfer. And just take a minute to note the baseline flows. You can see the flows. When we apply a transfer from bus A to bus I, do you see bus A and bus I? Bus A, do you want me to draw it for you? From bus A to bus I, the flow on every line will change. The PTDFs tell us exactly how much each line will be affected. Lines along the most direct electrical path will carry the most flow. So that's the reason you can see between I, G, H, and I, that's the most directive flow that we have. Now, you can see that the PDF percentage for a transfer from A to I, the transfer does not entirely go through one path. It splits across multiple paths according to their electrical impedances. Lines with high PTDFs are the ones that get congested first and limit how much power can be transferred. This is why market operators track PTDFs constantly. One large transaction can affect dozens of lines spread across a wide geographic area. So it's not just the limitations that we have, it's about cost as well. You can get from point A to point B, which is the shortest, but it doesn't mean that the shortest and fastest is the cheapest. Sometimes you're going to take the longer route to have less congestion, but it's going to be cheaper. It gives you the incentives of having that. A perfect example is that imagine you have a coal power plant in Amarillo and you want to buy electricity, but there is a wind plant in Lubbock that sells electricity like 20 cents cheaper, 20%, 30% cheaper, but you have a long transmission line. So you have to, calculate the cost and which one is congested. And sometimes it's cheaper to buy from Lubbock. Sometimes it's cheaper to buy from the coal power plant. Now, the line outage distribution factor, or what we call LODFs, LODFs, are used for contingency analysis. The reliability standard in North America requires that the grid remain stable after any single element outage. This is called the N-1 criterion. Instead of rerunning a full power flow for every possible line outage, LODFs, I'm just going to call it that, let us approximate the impact instantaneously. The LODF for a monitored line tells us if a contingency line trips, what fraction of its pre-outage flow gets redistributed onto the monitored line. And also the LODF depend only on network topology, not on the current operating state, so they can be pre-computed and applied very quickly. And this is the equation delta PL, a lot of LK of PK. Now, flow gates what are flow gates? Flow gates are how grid operators actually monitor the system in real time. A flow gate combines a monitored transmission element with a specific contingency. The contingent flow on a flow gate equals the base flow plus the LODF times the contingency flow. If a flow gate exceeds its limits, the operator must redispatch or curtail transaction. Independent system operators, or ISOs, like MISO, have hundreds of flow gates that are monitored continuously. The link shown here at the bottom, I would recommend that you read that and copy and read that one. It's already, again, it will be on the PDF slides on your Canvas. The links goes to official MISO list of coordinated flow gates. If you want to see what a real operational monitoring system looks like. Now, this map shows the NERC reliability regions. You've already familiar with this. I think I've shown this before multiple times. Now, NERC is the North American Electric Reliability Corporation. It sets mandatory reliability standards for the bulk power system in the US and Canada. Each region has its own reliability coordinators. If you notice the Texas, do you know which corporation manages Texas? Do you remember that? It was ERCOT, for Texas. And if you can look closely, actually the Panhandle area, which we live in, Amarillo, is a part of the SPPRE. We're not part of the ERCOT. That's the reason in the 2020 do you remember 2021? Yeah, shutdowns. Whole Texas was affected, but Amarillo, Lubbock, these parts were not affected because it's a different system. Now, as you can see, ERCOT, or the Texas system, is essentially its own island, and it's not connected to them, so they don't have a lot of power sharing. That's the reason we had that blackouts, because it was a very harsh winter. They didn't predict that. They didn't winterize the equipment, and the gas lines froze. The wind turbines, they didn't winterize them. They froze, so they had to have rollout blackouts. So they had to shut down to protect the grid. So again, ERCOT is its own island. It has very limited connections to neighborhood or neighboring regions. This was a deliberate choice to avoid federal jurisdictions at first, but it also means Texas has less ability to import emergency power from neighboring states during extreme events like what we had in 2020. So it comes with its own problems. Now, generation dispatch, we move to the second major topic, which is the economic dispatch. And you can again read faster than I can. So load is always changing, as you know, and there's almost always more generation capacity available than load. It must be that way. The question is, which generators do we use, and how much do we run each one? Imagine we have a variety, we have diversified actually generations. We have hydro, we have nuclear, we have renewable energies like wind, solar, we have gas power plants, emergency. But the cost of generation for each of them are different. And the other thing is, for some of them, you can't run them all the time, like wind, solar, hydro. You can't just open the dam, you're gonna empty it. And for other sources, you can't just turn them off like nuclear. It's not like you just flip a switch and you turn off a nuclear power plant. It's a long procedure. Some takes several hours, sometimes up to 24 hours to shut down a nuclear power plant. You have to do it in a safe manner. That's the reason you had the Fukushima. It's not like you can just flip a switch and turn it off, or Chernobyl, because it takes time for that core to cool down. It takes a lot of effort. You have to keep pumping water to keep it cool. You just can't, it's not like a gas generator that you can, cut the fuel and it's going to turn off. Nuclear generation power plants don't work like that. And for those reasons, economic dispatch is a very important part. And as I mentioned, for wind and solar, the answer is very simple. We use whatever is available because it's very cheap and you don't need fuel for it. Sustainable. And so since the fuel is free, we want to run them as much as possible. And for hydro, there may be limited water for the year, so you can't open it and let it just flow. And for fossil fuels, we want to minimize total fuel costs. So we don't want to run a coal power plant or a gas power plant on its full capacity. And the economic dispatch finds the optimal generator output at each instant in time to meet the load at minimal cost while respecting all constraints. Again, we don't want to run out of power. So that's the reason the economic dispatch is very important. Now, this is a very interesting graph. Traditionally, utilities had three categories of generators. We have the base load units, which are the large coal power plants and nuclear plants. These are the ones that run 24/7, 365. We almost never turn them off. They continuously run because it's very difficult to turn them back on or even shut them down. It takes sometimes up to 24 hours. They only shut them down for maintenance. These power plants have a very high capital costs, CapEx, but very low variable costs. So they run continuously at full output. Nuclear power plant, the initial cost is like $10 billion, but again, the fuel cost is very, very low. And then we have the mid-load units, smaller coal plants cycle on and off with the daily load curve. And then we have the peaker units, which are combustion turbines, and they have low capital costs but high fuel costs. So they only run during the few hundred hours per year when demand is high. And you can see that the load line is changing with the time of the day. So in the middle of the day, it reduces, but the baselines are always turned on. And then at the peak hour, which is usually between like 4 p.m. to 8, 9 p.m. As the peak hour, you would see the peakers jump in, and then we have the mid load. And this is around like 2, 3 p.m. or 2 p.m. or 1 p.m., something, depending on the region as well, which we have minimal. And this is early in the morning when everyone wakes up, turns on the coffee machines. So you can see that baseline is always turned on, the one down here. Mid loads just turn off and on. And then we have the peakers. So the mid loads and the solar, actually, the dot curve for the solar is inverse. So for solar, it looks like this, because you would have the maximum power in the middle of the day and then minimal power and no power at night. Okay, so the problem again here is that wind and solar have changed this picture dramatically, as mentioned. Since their fuel is free, they go to the top of the economic stack, which pushes fossil fuel plants to cycle more often than they were designed to. Now, another thing that we use in an emergency situation or in peaker situation is thermal or hydro. So one of the benefits of hydro is when you have a peak demand, you can just turn on a hydro or open the gates, water gates, and the valves, and you can generate power. Usually it takes a few minutes to kick in. So it's very, very fast and it's clean and efficient. And the other one is gas generators or turbines. So as mentioned, the two main types of generation we deal with are thermal and hydro. For thermal units, fuel is purchased continuously and the cost per megawatt hour is well defined. So short-term optimization is straightforward. For hydro, water is free but limited. Water used today cannot be used next month. You also have to manage reservoir levels, coordinate with upstream and downstream facilities, and satisfy environmental flow requirements for fish and navigation. So hydro optimization is a multi-period problem that spans months or even years. You have to nowadays AI is coming in, so they map the weather, when it's going to rain, if it's going to be a flash flood or something like that. So they map all that out. Now, in this course, we will focus on thermal units and wind because they make up the majority of the US grid and are more traceable for short-term optimization. And we will discuss that in the next lecture. I think it's enough for today. So that wraps up today's lecture. If you have any questions, just please email me. And again, before the final exam, we're going to have a review session in the final week. Yep, thank you so much and have a great day.